পাঠিয়েছেন? আপনি আমাকে পাঠিয়েছেন? ছেড়ে দিন, আমি নিজেকে পাঠাচ্ছি, ছেড়ে দিন। আচ্ছা, আপনারটাও চলে আসবে। Okay, very good afternoon to all of you. We are going to do two topics of inorganic chemistry today. One is hydrogen and the other is S block. So these are the two topics today. Okay, so the first thing that we need to know is that hydrogen has three isotopes. Okay, hydrogen has three isotopes. That is protium. This is protium. Okay, so we begin with hydrogen has three isotopes, protium, deuterium, and tritium. These are the three isotopes of hydrogen. So then we come to preparation of hydrogen. So zinc plus uh, dilute acid. Okay, zinc plus dilute acid is uh, giving zinc salt plus hydrogen gas. Okay, zinc plus dilute acid. Zinc plus dilute acid is giving zinc salt plus hydrogen gas. Then zinc plus aqueous alkali is Na2ZnO2 plus H2. Okay. Zinc plus aqueous alkali is Na2ZnO plus Na2ZnO2 plus H2. So this is the second reaction. So these are the preliminary two methods to prepare hydrogen. Zinc plus dilute acid is Zn2 plus hydrogen gas. Zinc plus aqueous alkali is Na2ZnO2 plus H2. Okay, then we come to electrolysis of water. So you know that water by itself is not a very good conductor, so we can add traces of either acid or base. So electrolysis of water will give hydrogen and oxygen. Okay, then more than 99.95% hydrogen is obtained by electrolyzing warm aqueous barium hydroxide between nickel electrodes. So these are the first four methods of preparing hydrogen. Okay, then we come to electrolysis of brine. So in the electrolysis of brine, at the anode you will get chlorine gas, and at the cathode you will get hydrogen gas. So this is method number 5, preparation of hydrogen by electrolysis of brine. Okay, then reaction of steam on hydrocarbons or coke. Reaction of steam or hydrocarbons or coke at high temperature in the presence of catalyst. Okay, now reaction of steam on hydrocarbons or coke at high temperature in presence of catalyst gives H2. So this is a hydrocarbon plus steam, the temperature catalyst, it gives giving CO plus H2. For example, methane plus steam at 1270 Kelvin in catalyst gives CO plus H2. This is an example of that. Now this mixture of CO and H2, this mixture is called water gas. Okay, the mixture of carbon monoxide and H2, that is called water gas. And it is also called syn gas. Syn for synthesis, because water gas is used to synthesize many other compounds like methanol, for example. So this mixture of CO plus H2 is called water gas. It is also called syn gas because it is used to synthesize, lot of compounds like, for example, methanol. So if you prepare syngas from coal, so this is coal. If you prepare syngas from coal, then this method is called coal gasification. Okay, so if you prepare syngas from coal, this method is called coal gasification. Now, suppose you want more output of hydrogen by this method only. Suppose by this method only you want more hydrogen. So what you have to do is you have to take the carbon monoxide and you have to react it with water at 673 Kelvin in presence of catalyst to give CO2 plus H2. The catalyst is iron chromate. So if you want to have a greater amount of H2, then you have to take CO plus H2O at 673 Kelvin iron chromate catalyst, and then you will get greater amount of H2. So that means the water gas carbon monoxide, you will have to further react it with steam. The carbon monoxide which you got in the water gas, you will have to further react it with steam, then you will get a greater output of hydrogen. So when you do that, that means when you take the carbon monoxide or water gas and further react it with steam to get the answer, then we call it water gas shift reaction. Okay, so that is called water gas shift reaction. Okay, so the hydrogen bond enthalpy is the highest for a single bond between two atoms of any element. So this bond enthalpy of hydrogen is the highest for a single bond between two atoms of any element, and Okay, so as I was telling all of you, the hydrogen-hydrogen bond enthalpy. Okay, the video quality is very hazy. Okay, okay, yeah. Thanks for your feedback. I have a suggestion. No, that's okay. That's not an issue. That's fine. Actually, see, no, it's okay. No problem. Thank you for your feedback. It's okay. If the video quality is hazy, then it's a bad thing. Okay. It doesn't matter whether it is my problem or your problem. It's a bad thing. Video quality shouldn't be bad. So I'll tell you, this video quality, it is actually affected by two things. One is, of course, the rate at which it is downloading on your device. Okay, one is the rate at which it is downloading on your device. The other is the rate at which it is uploading from my device. So the video quality actually depends on that. Of course, needless to say, it also depends on the handwriting of the teacher, which of course is not very good in my case. But the video quality depends on how fast it is downloading at your end and how fast it is uploading from my end. So I'll be very honest with you, my upload speed is highly fluctuating. I haven't been able to get a perfect upload speed till today. I mean, I would say that 7 times out of 10 it is good, and 3 times out of 10 it is not very good. That is the strike rate. Okay, so I think I will have to look at a permanent solution to that. So the upload speed from my side is bad at times, I will admit it, it is bad. So this upload speed is the upload speed is a variable from my end. I mean, I will not hesitate to say that 70% of the time it is good, but 30% of the time it is definitely below expectation. And I guess if I have to make a correction, then I'll have to completely switch off everything and switch it on again and hope that it works. And at your end, you can just try to refresh your page. So I think these are the only two things that I can think of. So one is that you can try refreshing your page, and the other is that if it is really bad, then I'll have to switch off everything and switch it on again and give it a try. But you are right, the video quality was hazy. Obviously you are right because you are watching the video, and the fact is that it all related to the upload and download speed. So I will not deny that yes, there has been upload speed problem from my side. Definitely I'll admit it. Okay, so let's see. I mean, if you feel that, oh, okay, fair enough. If refreshing your page is helping you, then that's good. Okay, thank you for your feedback. Thank you. So basically, the hydrogen-hydrogen bond enthalpy is highest for a single bond between two atoms of any element. So it's almost impossible. It's almost impossible that you will ever get hydrogen as an atom. Atomic hydrogen is virtually impossible to get. So it's always in the molecular form. So due to this fact that the hydrogen-hydrogen bond enthalpy is very high, the dissociation of hydrogen into atoms is only about 0.081%, and that is at 2000 Kelvin. I mean, such a high temperature. But if it is very, very high temperature like 5000 Kelvin, then it's about 95.5%. So 5000 Kelvin is way too high. So we don't really operate at these high temperatures normally. Okay. And one more thing is atomic hydrogen. which is produced by so atomic hydrogen, which is produced by dissociation of hydrogen with the help of electric arc, is allowed to recombine on the welded surface to generate 4000 Kelvin. So atomic hydrogen, which is produced by dissociation of hydrogen with the help of electric arc, is allowed to recombine on the welded surface to generate 4000 Kelvin. So if you allow atomic hydrogen to recombine on the welded surface, then you will get 4000 Kelvin. So this is very important. It has got application in welding. Okay, this particular feature has got application in welding. So potential energy curve for hydrogen. So this is the y-axis is energy, x-axis is internuclear distance. So you can see that when the hydrogen atoms are very close, there is repulsion. Okay, so the energy is very high, and when they are far apart, then there is hardly any interaction. But when the attraction and repulsion has a balance, that is when. So this is around 74 picometer, that is the internuclear distance between hydrogen atoms when they combine to give hydrogen molecule. So this is the distance when the repulsion and attraction balances and you get hydrogen molecule. Okay, now one important thing is You have to understand that hydrides can be of different elements. So hydrides, if they are group 1 or group 2 hydrides, okay, suppose if you have either group 1 or group 2 hydrides, then they are called ionic or saline or salt-like hydrides. So ionic or saline or salt-like hydrides are basically hydrides of group 1 or group 2. Then covalent or molecular hydrides, then electron deficient, electron precise, and electron rich hydrides. So what is the difference between these three? Electron deficient, electron precise, and electron rich hydrides. What is the difference between these three? So electron deficient is basically group 13 hydrides. So group 13 hydrides, they are electron deficient simply because they have a tendency to look for electrons to complete octet. Electron precise is group 14 and electron rich is group 15. So electron deficient hydride means group 14. Electron deficient is group 13. Electron precise is group 14 and electron rich is group 15. Okay, so these are called covalent or molecular hydrides. Why? Because they are all non-metallic, so covalent or molecular hydrides. Okay, then we come to metallic or non-stoichiometric hydrides. Now, metallic or non-stoichiometric hydrides, actually, this is applicable to transition elements, because in transition elements, what happens is that there are a lot of active sites. Okay, the surface of the transition elements has got a lot of active sites, and in those active sites, there is a possibility that the hydrogen atom may get involved over there. So that might result in a non-stoichiometry. So metallic or non-stoichiometric hydrides, because there might be a non-stoichiometry because hydrogen may enter into an active site and therefore the stoichiometry is disturbed. Okay, then we have ice at 0 degree. Okay, ice at 0 degree, it changes to water at 0 degree, which goes up to water at 4 degree. Okay, so what happens is that when you consider ice at 0 degree, so ice is basically has got a cage-like structure. Okay, the structure of ice is a cage-like structure, and in ice, what happens is that the structure is somewhat like this. So this is the structure of ice. So you can see that there is a hydrogen bonding involved. Okay. So this is the structure of ice. You can see it has got a cage-like structure because there is lot of hydrogen bonding. You can see these dotted lines are all for hydrogen bonding. So ice at 0 degree, it changes to water at 0 degree, and that changes to water at 4 degree. So ice at 0 degree, what happens? The density of ice is around 0.9. So at 0 degree, it becomes water. So when it becomes water, then what happens is that this cage-like structure starts collapsing, because this cage-like structure is for ice. So when ice changes to water, then this cage-like structure, it starts collapsing, and this cage-like structure, as it starts collapsing, the density increases. Okay, the density increases because volume goes down, and finally when the water reaches 4 degrees Celsius, the cage-like structure completely collapses, and that is why we say that water has maximum density at 4 degrees Celsius. So the cage-like structure is there at 0 degree. So after ice changes to water at 0 degree, the cage-like structure starts collapsing because it is changing from solid to liquid state, and by the time it becomes water at 4 degree, the cage-like structure completely collapses, and that is why the maximum density of water happens at 4 degrees. So this is called anomalous expansion of water. The fact that the density of water increases with as you change ice to water, the density increases, and then it further increases up to 4 degree before it starts going down. So this is called anomalous expansion of water. Okay, so suppose you are discussing hardness of water. So hardness of water is basically due to the dissolved insoluble salts of calcium and magnesium. So when you have insoluble salts of calcium and magnesium dissolved in water, that is what makes the water hard. So what exactly does hard water do? So basically what happens is that this is the formula of soap, C17H35CONA. This is the formula of soap. So soap and this is that insoluble salt which is present in hard water. So soap and this insoluble salt, it gives a precipitate. Okay, soap plus the insoluble salt, it gives a precipitate. So this is the precipitate, and in this precipitate, like I said, the metal is either calcium or magnesium. Now this precipitate, it is a precipitate, it doesn't dissolve. So this precipitate, it ends up as a scum. Okay, it is present as scum, which is very difficult to remove. So the fact that you have this precipitate, so this is called scum, and because of the scum and because it is difficult to remove, so that is the reason why hard water is not desirable, and therefore we must find a way to remove the hardness of water. Okay, so if the hardness of water is due to magnesium or calcium bicarbonates, okay, if the hardness of water is due to magnesium or calcium bicarbonates, it is called temporary hardness. So to remove temporary hardness, what you have to do, the magnesium or calcium bicarbonate, if you heat it, then it will get converted converted to magnesium hydroxide, and it will get converted to calcium carbonate. So if you just do ordinary heating like boiling, so this will get converted to magnesium hydroxide, this will get converted to calcium carbonate. After that, you can just remove these two precipitates by filtration. So once you have got these two precipitates, you can just remove them by filtration. So the next method is Clark's method. You add lime. So the next is if you add lime. So calcium bicarbonate plus lime is CaCO3 plus H2O. Magnesium bicarbonate plus lime is CaCO3 plus MgOH whole twice. So you add lime to the water, hard water. So if you add lime, then you will get precipitate of calcium carbonate and magnesium hydroxide, which you can filter off. So this is called Clark's method. You add lime, so you will get precipitate of CaCO3 or MgOH whole twice, which can be filtered off. Okay, then we come to the next one, how to remove permanent hardness. So permanent hardness you can remove by, permanent hardness is due to insoluble chlorides and sulfates. So you can remove it by washing soda or calgon or ion exchange or synthetic resins. These are the methods. So permanent hardness can be removed either with washing soda or calgon or ion exchange or synthetic resins. Okay, then we come to H2O2, which is a colorless pale blue liquid. Now, there is a very important type of question. There is a very important type of question which comes from concentration of H2O2. Actually, if you look at this reaction, H2O2 is giving O2 plus H2O. Okay, that is the breakup. Okay, H2O2 is giving O2 plus H2O. So by calculation, suppose this is 1 mole, so 22.4 liters, H2O2 will be 68 gram. So 22.4 liters of O2 is coming from 68 gram of H2O2. So 10 liter of O2, suppose if you are wanting, so it will be 68 into 10 by 22.4. So 30.36 gram of H2O2. So if you are ever told that the concentration of H2O2 is 10 volume, then 10 volume H2O2 is 30.36 gram per liter of H2O2. Okay, that is the concentration. Structure of H2O2 in the gaseous phase. You imagine that there is a book and this is the edge of the book. So the two oxygen atoms are here and this is the hydrogen on one side and hydrogen on other side. So oxygen length is 147.5 picometer, bond angle is 94.8 degree and this bond angle is 111.5 degree. In the solid phase, again the two oxygens are on the edge of the book. So the distance is 145.8 picometer. This hydrogen is on one side, 98.8 picometer. This hydrogen is on the other side. And this is in the solid phase. So this is the structure of H2O2. Okay, chemical action of H2O2, oxidizing action in acidic medium. Oxidizing action in acidic medium. So Fe2 plus in acidic medium H2O2 will oxidize it to Fe3 plus. Then PbS will oxidize to PbSO4. Reducing action in acidic medium. So MnO4 in acidic medium H2O2 will reduce it to Mn2 plus. HOCl will be reduced to HOCl will be reduced to Cl minus. Okay, then oxidizing action in basic medium. So in basic medium, Fe2 plus is oxidized to Fe3 plus, Mn2 plus is oxidized to Mn4 plus. And reducing action in basic medium. So iodine is reduced to I minus and MnO4 minus is reduced to MnO2. So this is a very important list, reducing and oxidizing action of hydrogen in acidic and basic medium. This entire chart has to be remembered. It is very important. Okay, first we start with S block. First we start with group 1 characteristic flame colors. Group 1 characteristic flame colors. So the flame color for lithium is crimson red wavelength 670.8. Sodium is yellow 589.2. Potassium violet 766.5. Rubidium is reddish violet 780. Cesium is blue 455.5. So these are the characteristic flame colors. Okay, then we come to the fact that cesium and potassium, they are capable of having the outermost electron excited, and that's why they have this characteristic color. So cesium and potassium are used as electrodes in photoelectric cells because of this. Okay, they have a tendency to tarnish in dry air due to the formation of oxides. Okay, so they have a tendency to tarnish in dry air due to the formation of oxides, and oxides react with moisture to form hydroxides. And one more thing is that they burn vigorously in oxygen. So lithium, in on burning in oxygen, lithium gives only monoxide, sodium gives monoxide, peroxide both, and potassium, rubidium, and cesium they give monoxide, peroxide, and superoxide, all the three. So lithium with oxygen is Li2O, Na plus O2 is Na2O2, K plus O2 is KO2. So lithium only forms monoxide, sodium can form monoxide, peroxide both, and potassium, rubidium, cesium can form mono, peroxide as well as superoxide, right? So superoxide, actually the problem is that why lithium and sodium cannot form superoxide, because the O2 minus ion is stable only in presence of large cations. Okay, the O2 minus ion is stable only in the presence of large cations. That is the reason. Okay, now we come to the very important diagonal relationship between lithium and magnesium. So both lithium and magnesium are harder and lighter than other elements. So that is number one. So lithium and magnesium react slowly with water. So they react slowly with water, and their oxides and hydroxides are much less solubles. Hydroxides decompose on heating. So lithium and magnesium react slowly with water. The oxides and hydroxides are much less soluble. Uh, and this hydroxides decompose on heating. And one more thing is that lithium and magnesium nitride, you can get it by direct combination of nitrogen, which doesn't happen with other elements. So as compared to the other elements of group 1 and group 2, they react slowly with water. Their oxides and hydroxides are not so soluble as others, and the hydroxides decompose on heating. And these two nitrides, you can get it directly by making it combine with nitrogen. Okay, then Li2O and MgO, they don't combine with excess oxygen to give superoxide. So Li2O and MgO, they don't have any tendency to combine with excess oxygen and give superoxide. That is point number 3. Okay, so both carbonates of lithium magnesium decompose easily on heating to form oxides and CO2. Solid bicarbonate is not formed by lithium and magnesium. LiCl and MgCl2 are soluble in ethanol. LiCl and MgCl2 both are deliquescent and crystallize from aqueous solution either as LiCl.2H2 or MgCl2.8H2. Okay, next we come to diagonal relationship of aluminium and beryllium. So like aluminium, beryllium is not readily attacked by acids due to the oxide film which is formed on the surface. So that is number one. So beryllium hydroxide dissolves in excess alkali to give BeOH whole 4 2 minus, just like AlOH whole thrice gives AlOH whole 4 minus. Okay, so BeCl to AlCl3 have Cl minus bridge chloride structure in Weber phase. Both are soluble in organic solvents, they both are strong Lewis acids, and they are both Friedel-Crafts catalysts. Okay, both beryllium and fluorine, they can form complexes BeF4 2 minus AlF6 3 minus. So both beryllium and aluminium can form complexes. Okay, now regarding oxides and hydroxides of group 2, except beryllium oxide, the alkaline earth metals burn in oxygen to form oxides of the formula MO, whose structure is rock salt structure. Why except beryllium oxide? Because beryllium oxide is covalent. That is why. The enthalpy of formation, the enthalpy of formation of the oxides is very high. That means they are stable to heat. and these oxides are ionic, and beryllium oxide is amphoteric. And MO plus H2O is MOH whole twice. That means these oxides react with water to give sparingly soluble hydroxides. Then the solubility, thermal stability and basic character of the hydroxides, it increases as you go down from magnesium to barium. Okay, then beryllium hydroxide can react with alkali. Beryllium hydroxide can also react with acid. So that means beryllium hydroxide is amphoteric in nature. Okay, except beryllium, all halides are ionic. And beryllium halides are covalent. And soluble in organic solvents. So except beryllium, all halides are ionic. So beryllium halides are covalent and they are soluble in organic solvents. And this is the chain structure of beryllium chloride in solid state. In vapor state, BeCl2 is a chloro-bridge dimer, which dissociates into linear monomer at around 1200 Kelvin. MgCl2.8H2O, CaCl2.6H2O, SrCl2.6H2O. So tendency decreases down the group. Okay, dehydration of hydrated chloride, bromides and iodides of calcium, barium and strontium can be done by heating. So this dehydration can be done by heating. and corresponding hydrated halides of beryllium and magnesium on heating suffer hydrolysis. And one more thing is that the fluorides are less soluble than the chlorides due to high lattice energy. Okay, next we come to the carbonates. So carbonates are insoluble in water. And they can be precipitated by adding either sodium or ammonium carbonate solution to a solution of So carbonates are insoluble in water and they can be precipitated by adding sodium or ammonium carbonate solution to a solution of soluble salt of these metals. So carbonates are insoluble in water. They can be precipitated by adding sodium or ammonium carbonate solution to a solution of soluble salt of these metals, and the solubility of carbonates decreases with atomic number. All carbonates decompose on heating to give CO2 and oxide. Beryllium carbonate is unstable, can only be kept in an atmosphere of CO2. So thermal stability increases with increasing cationic size. Then we come to sulfates. So sulfates are white solids. Stable to heat. BSO4 and BSO4 are readily water soluble. BSO4 and solubility decreases from CaSO4 to BSO4. greater hydration enthalpy of Be2 plus Mg2 plus overcomes lattice enthalpy. Therefore, sulfates are soluble. So, this is regarding the sulfates. Then we go to nitrates. So dissolution of carbonates in dilute HNO3. Magnesium nitrate has 6 molecules of water. Barium nitrate doesn't have any water molecule, it is anhydrous. So this shows that the tendency to form hydrated nitrate decreases down the groove. And all of them decompose on heating to give the oxide, just like lithium nitrate. So these are the chemical properties of group 2. So we have completed hydrogen, we have completed S block group 1 and group 2. So I'll conclude the meeting for today, and we will be resuming next Wednesday with another topic. Okay, I'll end the meeting. Thanks a lot. Bye all of you.